Okay, I can.
Okay.
Okay.
Sorry, I will ask you to allow me to share the screen.
Okay. Just a second. Yes, you can.
Thanks.
So while Marjan is opening his presentation, I should say some words about today's seminar. So we were planning this seminar, I think, for several months. And Marjan Cugmas is our colleague from the University of Ljubljana, our colleague and friend, I would say. And for quite some time, he's working on the topic of block modeling. And Marjan was making a presentation in our JASIM conference this April. And at this presentation, he will also tell about the further developments of this topic. And we are looking forward for this presentation, and we are very happy that Marjan today is with us. So Marjan, please, the floor is yours.
Thank you, Daria. Yeah, I have to mention also Aleš Žiberna, who is the co-author of this presentation. And I have also mentioned Anushka Ferligoy, who asked me to say hello to you. I forgot this.
Thank you.
Yeah, today I will talk about different approaches for block modeling, dynamic or temporal networks. You will see that in the recent years, many of these approaches were developed, and they try to solve the problem in different ways. And the question for an end user or for a researcher is which approach should you use? And I will try to answer this question by using Monte Carlo simulations. But first, let me just quickly summarize what a block modeling is. So by definition, a block modeling is a clustering approach for reducing large, potentially incoherent networks to a smaller, comprehensible structure that is easier to interpret. And the result of block modeling is, on one hand, a partition of equivalent nodes, and on the other hand, an image matrix which represents the links between and within the obtained clusters. I will also mention several times the term block, which refers to the links between two clusters and within one cluster. Here is an example of empirical network. I always show this picture. I really like it. It's not a real network. I just came out of my head. So here we have some nodes. These red colored nodes and some green colored nodes. You can see that these red colored nodes has very similar structure of links. They're not linked to each other, but they are linked to these green colored nodes. And these green colored nodes, on the other hand, has also very similar structure of links. For example, they are linked to each other and they are linked by these red colored nodes. So in the block modeling process, we string these red colored nodes because they have similar structure of links into one node, and we string these green colored nodes into another node. And this is then can be visualized by a graph in a graph form or matrix form. Here we have a graph form, and this is as a new matrix called a block model. So this is the block model where the nodes represents clusters of nodes from empirical networks. And we can also visualize the relationships between these different groups of empirical nodes. So this arrow here visualizes the fact that these red colored nodes tends to be linked to these green colored nodes. And we have a loop here which visualizes the fact that these green colored nodes from empirical network are very well linked to each other. So in social sciences, we are often interested in studying social phenomenon in time. When this is the case, we often want to analyze so-called dynamic networks, the networks that are observed at several points in time. In this presentation, I will talk about so-called snapshot networks, because several types of dynamic networks exist, and I will talk about snapshot networks. When we have snapshot networks, most of nodes are present at all time points, and the same relations are measured. One example would be a survey of friendships among high school students taken in February, March, and April. Here is an example. In that case, we would end up with 3 networks: one observed in February, the second in March, and the last in April. We have the same set of units, so the same students at all time points. Okay, some students might leave the network, some new students could join, but the majority of students or the nodes should be the same at all time points. And you can see that we measure the same type of relationship, which is a friendship. If you would analyze such networks in, I don't know, 2000, you would analyze these networks one by one. But today we will talk about block modeling of dynamic networks with these recently developed approaches, which takes into account the fact that the links between from consecutively observed networks are not independent. And it is believed that considering dependency between these ties from different time points can increase the validity of the results. But the aim of block modeling is the same as in the case of separate block modeling, which is to identify equivalent groups and ties among the identified groups for each time point. And further, you can also study how they change in time. Here is the list of approaches for block modeling dynamic networks that we found and consider in our study. Almost all existing approaches were included in our study. You can see that most of them were proposed quite not that long ago. The oldest is this approach proposed by Hu and Hiro in 2014. So these are all different approaches with very similar aim or purpose, but they differ in some characteristics. For example, most of these block modeling approaches are so-called stochastic block modeling approaches, which means that we assume, or the model assume an underlying statistical model, which is estimated by maximizing some kind of likelihood-based measure. And using these estimated models, you can do some statistical inference. On the other hand, there is a deterministic approach. We have only one representative of this approach. This is this one proposed by Žiberna, k-means based algorithm for block modeling linked networks. Here we use an iterative algorithm which searches for homogeneous blocks in terms of type values. According on how temporal dimension is considered, these different block modeling approaches can be categorized into 3 groups. We have state space models and conditional cluster probabilities models. Here, the parameter values or cluster probabilities in a current time point depends on the parameter values or cluster memberships in the previous time points. And on the other hand, we have so-called linked and multipartite networks. This is a collection of at least 2 one-mode networks and one two-mode network. This two-mode network links the nodes from different one-mode networks. So from different time points. In the context of, I just said this, and this link network is then block modeled as a single network with the restriction that the nodes from different time points cannot be clustered into the same cluster. And I put some special special informations for some selected block modeling approaches. For example, this one proposed by Hu assumes that the tie probabilities are conditional also on whether a tie existed in the previous time point or not. The dynamic stochastic block modeling model assumes within group ties probabilities are fixed in time, and these approaches proposed by Žiberna and also School enable weighting different parts of network. So the aim of my presentation today, and our study, is to empirically compare block modeling approaches, to evaluate sensitivity to the basic network characteristics of these block modeling approaches, and also propose some guidelines for choosing block modeling approaches. And we address these aims by using Monte Carlo simulations, within which we generated networks with different properties, for example, size, block model type, and so on. And we generated networks so that they look like real world networks. And we achieved this by considering some local network mechanisms when generating networks. And also we proposed an algorithm for generating networks so that the block model type and partitions are known in advance. This enables us to evaluate these block modeling approaches. So my presentation is divided into 2 parts. In the first part, we will take a look at directed networks. And in the second part, we will take a look for simulations for undirected networks. In this part, we were trying to generate the networks so that they would look like a co-authorship-like networks. And this second part is still in work. So I will present some preliminary results. So let me begin with these directed networks. We considered several factors. For example, network size. We have a scenario with small, 48 nodes, and large, 96 nodes. And then we also consider different block densities, stabilities of groups, different mechanisms, and block model types or transitions of block model types. I will explain these factors a little bit more detail in the following slides. But first, I have to mention that we assume 3 groups in all generated networks in this first part. So these are different block model types that were considered in this study. For all generated networks, we assume this block model type as an initial block model type. We have 2 cohesive clusters. So the nodes within these 2 clusters are very well linked to each other, and they are not linked to those from other clusters. And then we have also one peripheral group. So the units or the nodes from this group are not linked to anyone else in the network. And then we have 5 scenarios of block model type transition. The first, so they are ordered from the least to the most complex. You can see that the first one is the same as an initial block model type, which means that nothing changes. And then we have some other types of transitions. So you can see in this example that all links changes if we compare the initial block model type. This is a block model type at the first time point, and this final block model type, this is a block model type in the last time point. We also assume different block densities. We have two scenarios for this. The first is called low difference between the density of null and complete blocks. Here we assume 5% density in null blocks and 15% densities in complete blocks. And in the second scenario, high difference between the density of null and complete blocks, we assumed 5% density in null blocks and 25% in complete blocks. We have an example of cohesive block model type here and here with different block densities. You can see that these complete blocks are much sparser than these complete blocks here. So we can expect that block modeling approaches will work better here because the density between complete and null blocks is much different. And we also simulated different levels of group stability. So in time, different groups can merge and splits and so on. And we have 4 scenarios for these. The first is completely stable. Here, we do not have any merging or splitting of clusters. All clusters are the same in all 4 time points. And then we have very unstable case. Here, if we compare the first partition, so the clusters observed at the first time point, and the last partition from the last time point, these 2 partitions would be completely independent. And then we have also stable and unstable cases are somewhere in between. We generated these different partitions by randomly relocating a certain amount of units between the clusters. So in the completely stable case, we did not relocate any units, and here we relocated all the units. So I promised that we generated networks so that they look like a real world networks, and we achieved this by considering some selected local network mechanisms. We selected 4 very common social network mechanisms in social sciences. First is mutuality. This means a tendency to reciprocate links. Then we have popularity, which is a tendency to create links to those with the highest in degree, to the most popular ones. Transitivity as well, which is a tendency to create links to those who are liked by a friend. And outgoing share partner mechanism. Here we can explain this as a tendency to create links to those who like the same others. The strengths of these different mechanisms are summarized by the vector theta. We set all values to 1, which means that all these 4 mechanisms are assumed to have similar strength. Since these mechanisms are not completely independent, we cannot say that their strengths, that they have exactly the same strength, but so approximately the same strengths. We have 2 scenarios for this. First is without considering mechanisms, and the second one is generating networks with considering these mechanisms. In the first scenario, we set these values of theta to 0. This means that mechanisms are not considered, which means that the links will be created randomly within blocks when generating networks. But when we set these values of vector theta to 1, these links within blocks will be generated according to these local network mechanisms. I think it's time to present the algorithm that we propose for generating these networks. This is iterative algorithm, which means that we have to provide the number of iterations, which we set to 2,500 based on some preliminary analysis that we did. And we have to specify some initial parameters for this algorithm. Of course, we have to provide the initial network, also desired partition and desired image matrix with block densities, and then also mechanisms and their weights, and of course, number of iterations. And then at each iteration, we randomly choose a unit I, and then we calculate S containing the values of the selected local network mechanisms for the unit I. Then we calculate linear combination of the mechanisms. This is the part in which we consider these mechanisms, and then we add some randomness. And then considering a unit I, we determine a block B with the highest difference between the current and desired density. If the block is too sparse, then we establish a link to the unit with the maximum value of the weighted network statistic from block B. If the block is too dense, then we establish a non-link to the unit with the minimum value of the weighted network statistic from block B. Sometimes also occurs that block is just, the density of a selected block is just right. In that case, we randomly choose one option, either to establish a link or a non-link. And after 2,500 iterations, we return generated network. We have to apply this algorithm several times. First, we apply this algorithm on the empty network. So initial network is empty network. And then we obtain the network for the first time point. We apply the algorithm first on the empty network because we wanted to have the links, the links already from the first observation, first time point, to follow these local network mechanisms. And then we apply this algorithm again. So we end up with the network for the second time point, and again and again. So we end up with the network for the fourth time point. So we run this algorithm 1, 2, 3, 4 times, and we end up with 4 generated networks. Then we block model these generated networks. First, we use these separate block modeling approaches. This is what would you do if you would be doing this analysis before 2014. You would use either stochastic block modeling or k-means block modeling approach, or maybe generalized block modeling approach. But we use this stochastic block modeling and k-means based block modeling approaches. So we block modeled these networks observed at different time points separately. Here, we did not consider these temporal dependencies. And then we block model these generated networks by using temporal block modeling approaches as well. We use this each of these approach 2 times. First with default initial partitions, and then also with manual initial partitions, where as initial partitions, manual initial partitions, we took these obtained from separate block modeling approaches. In some cases, this might improve the results. So we end up with 2 sets of results for each approach, one for default initial partition and one for manual initial partition. And we further analyze the one with the best value of the optimized criterion and further analyze this one. And we we compare the obtained partitions by using the adjusted rand index. Since we got 4 values, so one for each time point of adjusted rand index, we will further interpret the mean ARI, adjusted rand index, across all 4 time points. For those who are not familiar with adjusted rand index is very commonly used to compare partitions. It is defined as the proportion of all possible pairs that are in the same cluster and all possible pairs that are in different clusters in both partitions. So we compare here the true partitions and the ones estimated by using these block modeling approaches. ARI is very nice because it is comparable among networks of different sizes and also number of clusters. The maximum value of ARI is 1. This indicates a perfect fit. This is what we want, so larger values. And in the case of random partitions, the expected value of ARI equals 0. It is very rarely that the value of ARI is negative. So this is, if we observe the value of ARI that would equal to 0, we would conclude that this block modeling approach is not that good. And here we have some results. So we have different block model change on x-axis. On y-axis, we have mean value of ARI. And by rows, we have block densities. First, we have low block density difference, and then we have high block density difference. And by columns, we have different sizes of networks, small network and large network. You can see that the problem is too hard, too difficult for all block modeling approaches when the networks are small and the difference between complete and null blocks is low. On the other hand, when we have large networks and high block density differences, the problem is relatively easy. So this is this case. The values are very close to 1. So more is happening here. You can see that in both cases, large networks, low block density difference, and small networks, high block density difference, dynamic stochastic block modeling perform the best when the block model type doesn't change in time. But when block model type does change in time, stochastic block modeling for multipartite networks seems to be the best. You can see that the dots are of different sizes here. This one is a little bit smaller, and this indicates the fact that it's in some cases this approach does not converge. It is not very often, but sometimes it happens that this block modeling approach does not converge. So let us take a closer look at the results. Now we will focus on large networks and high density difference case. So by columns, we have a block model types, transitions of block model types now. And by rows, we have the case with mechanisms. So when we consider mechanisms when creating links within blocks, and random case, so when the links within blocks are created just randomly. And on the x-axis, we have group stability and mean ARI on y-axis again. You can see that approaches works better when the links within blocks are generated randomly. So values are, mean ARI values are a little bit higher in this case than compared to this case. This might be because when we consider local network mechanisms, some local substructures might appear, and this might disturb the results. But you can see that all block modeling approaches produce excellent results when the block model type doesn't change. This is this part. But if block model type does change, then stochastic block modeling for multipartite networks and stochastic block modeling for linked networks, these two produces very good results in all cases. Again, this stochastic block modeling for multipartite networks might have some difficulties with convergence here. But again, not very often. Now let us focus to the case with small networks and high density difference between null and complete blocks. You can see that. Yeah.
You have to wait a little bit, I think.
Yeah. I'm sorry for this. You can see that the stability of partitions affects all approaches which consider all time points simultaneously. So these temporal block modeling approaches. But it does not affect approaches for separate block modeling. These are the stochastic block modeling and k-means. You can see that here, for example, quite clearly that they are not affected by the stability of groups. But these approaches that consider this temporal dependency are affected with group stability, but you can see that their corresponding RE values are quite larger, which means that you would still benefit by using these temporal block modeling approaches. Again, dynamic stochastic block modeling approach produces far best results, especially when mechanisms are considered and when block model type does not change. But if block model type does change, then this stochastic block modeling for multipartite networks is quite efficient, followed by this state space models block modeling approach, which might be used if this stochastic block modeling for multipartite networks would not converge. And then finally, we have the case for large networks and low density difference case. You can see that dynamic stochastic block modeling approach is again the best, and otherwise the best when block model type does not change, and otherwise stochastic block modeling for multipartite networks produces very good results. So my conclusions and recommendations for you would be always use prior knowledge and run some separate analysis as a preliminary analysis to confirm your knowledge about the network. And then second advice would be try with different initial partitions, because this can increase the validity or the quality of your obtained final partitions. And do not forget to use stochastic block modeling for multipartite networks, and dynamic stochastic block modeling depends whether you assume a block model type that change or not in time. Now I will talk about undirected networks. The inspiration was the empirical co-authorship networks, because in the future, we would like to analyze such networks of Slovene researchers. And the question is, which block modeling approach should we use? So we have some prior knowledge about these empirical networks, because in 2015, me and Nusha and Luca Kroneger ran some analysis on co-authorship networks on Slovene researchers. And we found that, okay, by definition, we have symmetric ties when analyzing co-authorship networks. We want to analyze them in 2 time points. But what is really valuable is that we have quite large percentage of newcomers and outgoers. And we also found very typical multi-core semi-periphery structure, which is visualized here. This is an example for sociology. And this is a network visualized in a matrix form. So in rows, we have researchers, and by columns, we have researchers. And if there is a dot, this means that two researchers published at least one bibliographic unit together. And these two networks are drawn in line with the block modeling solution. We block modeled each time point separately. And you can see that we obtain these very dense complete blocks on the diagonal. These are called cores. So these researchers collaborate to each other quite systematically. And then we have this part of a network called semi-periphery. The researcher in this part do collaborate with others, but not in such a systematic way. And then we have this periphery. The researchers here publish something in this time point, but alone or with researchers from abroad. So we then visualize this, the stability or similarity of these two partitions from these two time points with this figure here. We have these black rectangles visualizing the cores. Then we have this orange for semi-periphery, for periphery, and these incomers and outgoers. Quite large share of incomers. So the number of researchers is growing in time, but some also retire or or stop publishing. But what is interesting is that we have quite a lot of dynamic, a lot of splitting and merging of groups in time and so on. So we have relatively unstable clusters. So to generate networks, we had, and to perform these Monte Carlo simulations, we had to determine some factors. And we were looking at these empirical networks when doing this, but we also wanted to reduce the number of different combinations so that the simulations will finish till today, actually. And yeah, this is a preliminary study, so we will increase this different number of considered factors in the future. So we have the case, the first factor are newcomers. We have two scenarios. First is without newcomers, and the second is with 50% of newcomers compared to the network size in the first time point. Then we have outgoers, two scenarios, 0 and 20%. Then we have network size. This is the same as in the first part of presentation, 48 and 96 nodes. And then we have different levels of stability of groups. This is also the same as in the first part of my presentation. I leave some factors to be the same as in the first part, so that so that I will be more consistent, so that it will not be so many new informations for you. And then we considered also two scenarios for these mechanisms. One is without mechanisms, and one is with mechanisms with the same, approximately the same strength. We have only one type of transitivity here because we do not have outgoing shared partner mechanisms, because we have symmetric networks now. And then we have some fixed effect. We have 3 groups in all generated networks. We consider cohesive block model type, which means only this part here or here. We did not consider semi-periphery or periphery. And also we did not consider these complete blocks outside the diagonal. These are called bridging cores, just to simplify it a little bit, these simulations. And we have only one scenario for block densities, 5% density in null blocks and 25% density in complete blocks. And this is the algorithm for generating networks. It's very similar to the previous one, but with some new components. You can see that it's still an iterative algorithm, but we a little bit increase the number of iterations because of these newcomers and outgoers. And you still have to specify some initial parameters. For example, initial network, desired partition, desired image matrix with block densities, mechanisms and their weights and number of iterations, and two additional things, which is the number of incomers and outgoers and the minimum cluster size. We decided to consider this minimum cluster size so that we would not end up with empty clusters. So only practical reason. And at each iteration, we randomly choose a unit I, then we calculate as with the values of the selected local network mechanisms for that unit I. We calculate linear combination of the mechanisms, and then we add some randomness. And then considering a unit I, we determine a block B with the highest difference between the current and desired block density. If the block density is too dense, then we establish a non-link to the unit with the minimum value weighted network statistics from block B. If the density is just right, then we randomly select this option or this option. But if the density is too sparse, then we will propose a new link. And only this part is new, and this one. So let us denote a unit. So now the block density is too low. A block is too sparse, so we want to create a link. So we cannot just create a link because we are generating symmetric networks, and the other one have to confirm the proposed link. And this is the idea of this part. So let us denote a unit with maximum value of weighted network statistics from block B as unit J. And then we calculate a weighted network, calculate a linear combination of the mechanisms between the unit J and all other units. And then with this probability, which is calculated based on ranks of this linear combination of the mechanisms, we establish a link between I and J. And then we consider whether we want to have incomers or departure outgoing units. And then after many iterations, we return generated network. Now I will say a few words about these incomers and outgoers. I use departure here, which is a synonym for outgoers. I couldn't decide which words to use, so I decided to use outgoers, and I forgot to change this one. So newcomers and outgoers. It is randomly determined at which iteration units join or leave the network. And at the beginning, we have to specify the number of those incomers and outgoers. So at each iteration, we check whether there is a time for a new unit or whether there is a time for a unit to leave the network. If it's time for a new unit, then we add a unit to the network. When we add this unit to the network, the unit does not have any link to the other units. And we add, so a group to which we add a newcomer is chosen proportionally to the group size. And if it's time for a unit to leave the network, then we remove the unit from the network. All the units have the same probability to be removed the network, but there are two exceptions. Newcomers, so newcomers cannot be removed from the network, and the units from groups with the size equal to the minimum group size. So if removing a unit from the network would cause very small cluster or group, then we do not remove this unit, but remove some other unit instead. And then we generated networks for the 2 time points only. In the future, we might change this, but for now, we have just 2 time points. We start with empty network as an initial network, and we apply this algorithm for the empty network. So we end up with network for the first time point, and then we apply this algorithm again, and we end up with network for the second time point. So we have two observations. Then we again apply these separate block modeling approaches, stochastic block modeling and k-means-based block modeling. And then we apply these now well-known temporal block modeling approaches. We did not use this proposed by Hu and Hiro because they do not enable considering incomers and outgoers. So we have only 4 different block model approaches, block modeling approaches. We run them 2 times, first with a fold and then with manual initial partitions. And then we evaluated these results in the same way as in part 1 of my presentation. So we calculated ARI, higher value of ARI means better partitions. And here are the results. First, let us take a look at the results for large networks, because they are simple. You can see that all approaches work very well when you have large networks, for example, more than 96 units. But this might also be an indicator that we should think about calibration of the values of the considered factors so that we would observe larger differences among different block modeling approaches. And this is the case for small networks. You can see that we have a slightly worse results in the case with mechanisms. This was expected. And it seems that dynamic stochastic block modeling works better when the mechanisms are considered, which we also saw in the first part of my presentation. You can also see, oh, I forgot to explain this picture. So we have mechanisms in the first row and random in the second row. And then we have this stability of partitions on x-axis, and on y-axis we have mean ARI, and then we have different columns for different amount of incomers and outgoers. Here we do not have any incomers or outgoers. Then we have the case with outgoers only, and then we have the case with incomers only, and then we have the case with 50% of incomers and 20% of outgoers. You can see that incomers, you can see this here, for example, increase the mean value of ARI. And this might be because incomers increase the size of network, and these block modeling approaches works, especially stochastic block modeling approaches, works better when we have larger networks. On the other hand, outgoers here worsen the results, and we do not worsen the results. So in the case of mechanisms, worsen the results, especially for this dynamic stochastic block modeling approach, and for almost all in the case when we have random case. We do not know yet why is it so. One explanation might be smaller network, but this does not explain everything. There are still some questions that we have to further dig in. However, all approaches produces comparable results. In the case of incomers and outgoers, this is this panel, mechanisms, and very unstable partitions. This is the case which is the most similar to our empirical case. So the answer, which block modeling approach should we use, might be, for our case, it doesn't matter because all produces quite similar results. But in general, you can expect more similar results among different block modeling approaches when you have larger networks. And I would suggest you to use dynamic stochastic block modeling approach if you do not have any outgoers and if you expect quite stable clusters in time. But otherwise, use stochastic block modeling for linked networks. And I just told you that in the case, for our particular case, it might be that it doesn't matter which approach would we use, we would end up with very similar results. Yeah, this is a warning that this is a work in progress. Still, there is quite a lot to be done. In the future, we will we will send the paper for the first part to the journal Social Networks, and then we will continue with this second part. We will upgrade this study with additional network characteristics, maybe more time points, and then we will apply one or several of the block modeling approaches. We'll see which one will be the best on empirical co-authorship networks. We quite well know these networks now, so we will be able to say something about the validity of this block modeling approach, and then we will also consider new data. So as you can see, these data are until 2010. We have now data till 2020, so we will then also extend this study into 3 time points or something like that, but definitely with new data and possibly using this temporal block modeling approach. So this is all I had to show. Yeah, thank you for your attention. I hope that you didn't fall asleep. And if you have any question, I will be very happy to try to answer. Maybe I will not know how to answer. In that case, I will maybe have to improve the simulations. If you will have any idea or, I don't know, outstanding comment.
Thank you very much, Marjan. So, dear colleagues, do you have any questions? Okay, if you are thinking on your questions, probably I can ask some. First, I would like to ask some questions for clarification. And I wanted to ask, considering your analysis of co-authorship networks, you said that that first analysis was done without considering temporal dependency. So can you say again what exactly it means, so that you didn't they didn't consider the connections between the same nodes?
Yeah, in time.
In both networks.
Yes. So, for example, here, maybe. So let us assume that this is a co-authorship network. So we have networks for different time points, and we can first block model this network, and then we can block model this network, and then we can block model this network. This is all good. But we have additional information in this data, which is not considered when analyzing networks in such a way. And this information is that these nodes are the same people. Okay? And this means that, for example, this link and this link, this link and this link and this link are not independent in time. They're not independent because they are between the same people. And we can consider this dependency when using when block modeling. So essentially, so these different approaches consider this dependency, time dependency, in different ways. So if I simplify a bit, I would say that they put some constraints on clustering, and these constraints considers these dependencies. So here we did not consider these dependencies. So also in this block, also here we have the same, some units are the same in time. And we did not consider this fact when analyzing these co-authorship networks. And we will try to consider this in the future. And we will see whether this can provide us with different, maybe more valid results or not. So this considering temporal, I am quite confident to say that considering temporal dependency cannot do any harm.
Yes, of course.
So yeah, this is also seen, for example, here. So if you consider temporal dependency, you in most cases you get better results. Yeah. And in worst cases, you can get the same results with considering or not.
Yeah, it's really a very nice work. I'm just amazed how structured it is, and I think I already told you about that. I really like that slide with different approaches to block modeling, to dynamic networks, which really helps a lot to somehow differentiate between these different ways to make the analysis. Okay, thank you very much, Marjan. I also have another question. Probably it's less for clarification, but like for discussion. So for your first part, it seems like these approaches, I mean, how I understood it, that these approaches work better for when the networks are changing randomly, but not according to mechanisms that you proposed.
Yeah.
Am I correct?
Yeah. So when there are some local network mechanisms that affect creating the links within blocks, in that case, the results are not that good compared to the case in which the links are created just randomly. I would say that more realistic scenario, especially for social sciences, is this with mechanisms. Yeah, so I don't know, I don't have any example in which we could observe these random links within blocks actually, while I have many examples for this case with mechanisms. So this is very common, and these mechanisms can produce some substructures. For example, you have a cohesive group, and then within this cohesive group, you can have two cohesive subgroups, or you can have core periphery within this group, or and so on. Some very tiny, small substructures, but these, yeah, probably these are the ones that causes that the results are not that good when the mechanisms are present.
Yeah, but thinking from the side of social science, it's, I mean, if we are analyzing some social processes, it seems like the links are not changing randomly, but exactly according to mechanisms. And so based on this analysis, we can conclude that if we are analyzing social networks, I mean, in social sciences, so it is probably to use small networks. So use these approaches for small networks, and then we will get better results.
For large networks. So if you have larger networks, then you have better results. Yeah.
Anyway, this okay.
For example, if you compare these two, the results for small and large networks, you can see in both cases that values are are larger in the case of larger networks. Because you have more information to estimate the model. Yeah, if you can.
Yeah, I was just thinking about this random and mechanisms effects. So that it seems like you showed the slide that for mechanisms works better for small networks. So that's why I made that conclusion.
No.
No?
No. In general, in general, you can see so large networks, high density, small networks, and large networks. In all cases, the values in the first row for mechanisms are lower than compared to the second row for the random case. So in all cases, when you have local network mechanisms, these block modeling approaches will not be that good, that efficient, and also larger network means better results.
Okay.
Yeah.
I just mean that exactly when we are analyzing our networks, we are exactly dealing with social mechanisms, but not randomness. So that's why.
But you cannot. I mean, you can do nothing about that. So I think that you know, when people try to compare these block modeling approaches or analyze some that kind of approaches, they usually generate these random networks or links within blocks just randomly. So this case. And I think that one very important added value of our study is that we try to consider also local network mechanisms, which is very more realistic. And we have shown that these have important implications for the results. But as a researcher, the one who is want to use one of these block modeling approaches, he or she cannot choose between mechanisms or random because the network is as it is. You can, yeah.
But probably I just thought about it right now that you can analyze your own network, which you suppose has mechanisms, and also you can construct random network and compare your own network to this random network.
You could do this. We were doing this to evaluate the fit. I mean, how well a given block model fit the empirical data. So we run block modeling approach once on the empirical network, and then we run this block modeling approach many times on many randomly generated network. And then we calculated the mean value of criterion function, and then we just put 1 minus the criterion function obtained on value of criterion function obtained on empirical network divided with the mean value of this criterion function obtained on randomized networks, and we use this as a measure of fit. So yeah, this could be done to say something about the fit, to the global fit of a block model to the data.
Okay, thank you. We have a question from Alexander. Alexander, please.
Hello.
Hello.
Marjan, thank you very much for the great presentation. I would like to ask one question to clarify one thing. When you did, sorry, I have some problems with English speaking. Well, Was the number of simulation steps the same for small network and large network, or it was proportional to the size of network?
It was the same. I think that you're asking about these parameters. These were the same for large and small networks, but were set to quite high number of. This is especially relevant for these two. You can see that the number of repetitions was set to very large value, so it should be sufficient for both small and large networks.
Oh, okay.
Yeah. You're welcome. Yeah, but it's true. For example, these two are quite time consuming, and especially with large networks. So, and while these two are I'm not sure about Bargen, but I think that also this one and these two are faster compared to this proposed by Žiberna and Škul. Which means that if you have very large networks, you would not have enough time to estimate them. Very large means, I don't know, 500.
What about the process of changing the network?
You mean?
Went from the first random network, then the second stage, the third stage, and so on.
You mean?
Yes, I mean the singular. Yes, I mean
this one,
yes,
or this one, or this one.
Yeah, when you apply an algorithm
several times,
changing ties in networks. Yes, here. Was the number of changes the same for networks of different sizes?
Yes, so two things. First is the number of iterations. This was 2,500 in this first part. It was the same for smaller and large networks. We ran some simulations and we were observing the number of the amount of errors, so the difference between ideal and observed block densities. And we also ran ergom and to observe whether so we observe these errors to observe whether the densities stabilize within blocks. And then we also run ergom to verify that the local network mechanisms are actually present. So we found out that 2,500 iterations is enough for large and small networks. And then we have this part here. Here we apply this algorithm 4 times in all cases, small and large networks, because this is more related to how many time points we want to generate it. For each time point, we apply this algorithm once.
Oh, okay, understood.
Yeah. So we first set empty network as an initial network for this algorithm, and then we end up with one generated network. And then we took this network as a network observed in the first time point. And then we apply this algorithm again, but this time we use as an initial network this network from the first time point and so on.
And each time you had 2,500
iterations. Yes. Yeah.
Okay,
Marjan, and talking about the size of network, so you said that you are thinking to use this approach to study the collaboration networks, but we can propose that they are quite large. So will this approach be able to analyze the thousands of networks?
I didn't understand you. What did you say that I proposed?
You said that you are going to analyze the collaboration networks. So probably the third part from 2010 to 2020. And so like you will have 3 time points of collaboration in your data. And so I suppose that the size of these networks is quite large.
No,
so
it's
will
not
this
that,
approach be able to?
We will see. So this is sociology example, and we have, I don't know how, it's not that much here. The larger network for this study was, I don't know, around 300 nodes. So I do not expect that the number of nodes researchers will be much higher.
Okay.
We'll see. Also, we will have to decide whether we will analyze on the level of scientific disciplines or on the level of scientific fields. For this, here we used generalist block modeling, which is much slower compared to these stochastic block modeling approaches, and maybe also k-means block modeling approach. So this, so maybe we will be able to analyze slightly larger networks now, and also we have better computers now. But it's not 1,000 nodes, and it's much, maybe not more than 500 or 300 for the larger scientific disciplines, I think. We are a small country. Yeah, we are 2 million, approximately 2 millions of Slovene people. So if all of us would be researchers, then yeah.
Okay, dear colleagues, do you have any other questions or comments? I also wanted to ask you a question about, you said that if we think that, so we can choose one or another method of block modeling, considering the stability that we expect in our network. And how can we know about the stability, how stable it is? Because usually it's a kind of research question. So is this community stable or not stable? So do you use any other methods to first we look at the data and understand if it is stable or not?
Now, one way would be, so if you don't have a prior knowledge, would be to run separate analysis and then run one approach that is sensitive to this stability of groups. For example, dynamic stochastic block modeling, and also run this, for example, this stochastic block modeling for multipartite networks. And if you would observe very similar results, for example, between these approaches, then you can expect that these are quite unstable. Otherwise, or quite stable. It depends whether you compare them with
what results
with this separate or temporal. And then based on this, you could maybe choose one or another. You can also compare different, but not all of them are comparable. Maybe you can also compare these values of criterion functions, but not all of them are comparable. So you have some limitations here. Yeah,
are you planning to make some guide afterwards? Like if you have this kind of data, so go to this kind of block modeling. If you have something like this, go to, some kind of scheme where you can show the ways how to navigate if you are not really in block modeling, but you would like to use some type of it.
I was thinking about this, but then now I'm looking whether I want just to check something so that I will not lie too much. I was thinking about this, and what I figured out is that it is either this dynamic stochastic block modeling approach or stochastic block modeling approach for multipartite networks. I would suggest these two. One of these two is very good. Is appropriate. You do not, okay, so in some cases, also this approach perform quite well. But usually when you analyze empirical data, you do not know, as you said, how stable the partition is and block model type and so on. But in most cases, this and this are the best. So the risk is the lower when you use this one or this one. And now you can see that the fit of this, that the ARI value of this and this blue and this orange is very similar when you have very unstable case in almost all cases. So this is why my idea was, when you don't know how stable is it, do this and this, and if the results will be similar, then it doesn't matter which one you use. Otherwise, use this dynamic stochastic block modeling. You can also calculate ARI between the consecutive time points. If you apply this dynamic stochastic block modeling, and then you calculate ARI between consecutive time points, and you observe a high ARI, this is an indicator that this approach is appropriate. If you would calculate low ARI, then maybe you should try with this one.
Okay.
Yeah. And you can also check you can also draw the block model type for each time point and see whether it changes a lot or not that much. One important thing to consider is that dynamic stochastic block model assume where is it? That yeah, here it is. Type probabilities are conditional on whether within group ties probabilities are fixed in time. This means that this block modeling approach assumes that block model type does not change in time. This is why we have the very large values in this A panel, but in fact it is not that strict. This, if I'm more precise, this only means that the blocks on the diagonal are the same in time. So the block model in fact can change in time, but the diagonal blocks must remain the same, which means that the within group densities shouldn't change in time. If they don't change in time, then the assumption is met, and this dynamic stochastic block modeling approach is the best. I was talking about when block model type doesn't change here, because this is the only case in which we also have some, sorry, I will take it back. It's not the only case in which block densities does not change, because we have also B and C. But obviously, these other block changes can also affect this approach, dynamic stochastic block modeling, even though this is not an assumption. Maybe I overcomplicated this. So my advice is to use dynamic stochastic block modeling or stochastic block modeling for multipartite networks, and then calculate all kinds of ARI. So ARI between consecutive time points. If these ARIs are large, then I'm quite confident that dynamic stochastic block modeling is okay. You can also draw the networks, block models, and observe and calculate maybe the within group densities to see whether block model types does change a lot in time. All this can be done. If it doesn't, then again, dynamic stochastic block modeling is the most appropriate. Yeah, and if you have any theory, so for example, we generated this, we analyzed these these networks for almost 70 scientific disciplines, and in all scientific disciplines we observe this typical block model structure, block model type. And there is also the theory behind that support this block model type. So here, if we will repeat the analysis, we can be quite confident that this is the right, the block model type doesn't change in time. Yeah.
By the way, I really like these pictures. It seems like modern art.
Yeah, you can see that. Yeah, in the first half of my presentation, the pictures are not that nice because well, I didn't want to make them very nice to show that this is still a work in progress. Yeah.
Okay. Thank you, Marjan, so much.
You're welcome. Thank you for the invitation.
Yeah, dear colleagues, do you have any other questions, comments? Okay, I think it's for the majority of us, it's a kind of lecture. So it's we need to process it and then probably to get some questions. And actually now we are working on the project devoted to the collaboration structures of the Russian sociologists. So I'm thinking that somehow we can also analyze the stability of these structures and to somehow evaluate them in time. So we are looking at your works. Yeah, and probably once we will be able also to present something, a kind of something with these approaches.
Great.
But before this, we will have to make to have some consultations with you, Marjan.
I just wanted to say that if you will need any advice or maybe technical help or anything like that, I'll be glad to help.
Thank you so much.
Yeah.
Okay, dear colleagues, and we actually fit the time that I said that we have about 1 hour and a half, and now we have exactly this time, so we are good. So Marjan, thank you very much for this very interesting and nice presentation. And it's always, I should say, it's always a pleasure to see how you present things, so how you explain things, even such difficult things as block modeling and different approaches inside block modeling. So we really appreciate that you came to our seminar, and we wish you really to get great results in this work and to publish it in social networks, as you said.
Thank you.
Yeah, so that we will read it and cite it.
I will send the paper this week.
Okay, great. So good luck with it.
Yeah, thank you.
Okay, so now I think we can stop the recording